which is about caching on GPUs.
I don't think I actually see my, oh, there we go.
We can see it here.
Yep.
Yes.
It's clear now. Awesome. All right. Hello, everyone. My name is Keshav from the University of Southern California. And today I'm going to be talking to you about something slightly different from what you might have listened to over the past few days. Kind of more of a systems-y side of things, and how system solutions can enable scale and recommendation models. So this is look-ahead caching for scalable training of recommendation models. So we primarily focus on deep learning recommendation models that in general are composed of compute-intensive neural networks like MLPs to learn continuous valued attributes and memory-intensive components of neural networks to learn categorical attributes, which are embedding tables. And what we noticed is that usually when compute-intensive components are required to be sped up, data parallelism is a common paradigm that's employed. And when memory-intensive components are required to be accommodated across GPUs, model parallelism is a common paradigm that's used. Now, the issue here is that in a model that requires both, the number of GPUs that data parallelism requires is often a lot less than the number of GPUs the model parallelism requires. As a result, what ends up happening is that this number of GPUs that the entire training infrastructure requires is usually determined by storage concerns and less by compute requirements, right? This is a problem because too many GPUs end up being used mostly for storage without any relation to how many GPUs are required for compute. Ideally, we would have compute dictate the number of GPUs that we require and not storage concerns. If we could, we would prefer to store large embedding tables in cheaper, lower bandwidth memory like CPU or even some kind of NVMe and have just the compute bound parts of the network stored in GPU memory. We have to be careful, though, that any solution to this problem doesn't result in any considerable degradation in model or computational performance. So before we move ahead with some observations that inform a solution, there is one term that I will refer to throughout the rest of this talk, and that is the notion of a look-ahead window. And essentially, a look-ahead window is just a sequence of batches. So anytime I mention a look-ahead window of size n, all I mean is a sequence of n consecutive batches that appear in the training set. So what we notice is that for any large embedding tables, which tend to be predominantly the case for industry scale recommendation models, is that for any given look-ahead window and of fairly large sizes, that the number of rows accessed in that table across that look-ahead window tends to be much smaller than the actual table itself, right? So as we can see on the right, given a look-ahead window size of 100 and a batch size of 2048, which can be thought of effectively as a batch size of 20K, the number of rows that are accessed in the table across all entries in the effective batch of 20K data points is only 0.7% of the table. And for a different table, it's only 0.15% of the table. This essentially is saying that we don't need the whole table in a GPU to be able to train for at least for these 100 batches in the look-ahead window. So ideally, we'd like to maintain only such a working subset of either 0.7% of the table in this case, or 0.15% of the table in the case of the second table in the GPU. If we were able to do this and do it in a way in which performance wasn't hit too badly, we would be saving a lot of space in GPU memory. So the way we do this is through a caching mechanism. And one thing for those of you who are who tend to deal with caches more regularly is that you might be thinking is, oh, if caching is being proposed as a solution, there has to be some notion of locality of access, which is something that's interesting with recommendation models and table lookups, is that there actually is no locality that can be assumed. In fact, what we notice is that accesses are pretty random. There's no correlation between one batch's accesses to a table and another batch's accesses to a table. How we deal with this will be explained a little bit later, but essentially all we do to reduce the footprint in GPU memory is to store a cache of the embedding table. So cache of an embedding table is just a smaller embedding table. And to be in line with standard terminology from memory systems and computer architecture, we organize the cache into sets and ways. And if we have S sets and ways in a specific cache, the number of rows in the cache is just S times W. So effectively, S times W is usually a lot smaller than the R entries in the main table. So any index I that's been being looked up in the original table will map the index I modulo S in the original table. And then once the set is chosen, the way within that set is chosen at random to finally place it in the row in the cache. So like I mentioned, we need to have no degradation in not just model performance, but also in computational performance. We need the system to be responsive, have low latency, and essentially seamless, right? So the way we achieve this is through three processes that work asynchronously together and communicate with each other with two queues, the look ahead and the write back queue. In our system, the three components that are of the model that are trained and directly updated through gradient-based optimization are the MLPs, the caches, and the victim tables. And I'll explain the victim tables a little bit more in detail a little later on. So just to give everyone an idea of what each of these processes is doing, so you have a mental map, I'm going to run through illustrations of examples for each of these processes. So the first of these is the prefetching process, and the job of the prefetching process is to essentially process look-ahead windows ahead and push only what is needed, what it deems is needed for across the look-ahead window into a queue to be consumed. So what it does is it loads a number of batches from disk and splits them up into look-ahead windows. So in this example, we have a batch size of 2. So each batch is essentially just looking at 2 indices, and we're just pretending we have a single embedding table, right? So what this process does is it look across each of these look-ahead windows and compute the unique indices in these look-ahead windows, right? So in this case, we only look at the unique indices and fetch the embeddings corresponding to those indices from the CPU resident embedding tables. E1 through EM, in this case, just E1 because we're only focusing on a single embedding table, are all CPU resident. Once it's pushed all the embeddings into the look-ahead queue, it just repeats this process until it's exhausted the data set. It has no awareness of what the other processes are doing and is truly asynchronous from all the other processes. The next process is the caching plus training process, is perhaps the most involved process. And the first step with this process is to cache entries. So it does so by first pulling entries, and you have indices and the embeddings corresponding to the indices. It filters out which indices are already in the cache. This is facilitated through a tag structure, which we call occupancy table, which basically lets an index know whether it's already present in the cache. It gets the missing indices, which need to be cached, and then caches those indices in the cache structure present in GPU memory. During this process, there are embeddings that are evicted that are no longer needed for the next set of batches in the look-ahead window, and those evicted embeddings are pushed into the write-back queue to be consumed by the eviction process. So as I mentioned previously, once a set is chosen using the modulo hash, the way within that set is chosen randomly for performance reasons. The downside of this is that we have the potential to generate what we call victims. So in this example, we have missing indices 1 and 4, both mapped to the same set and way within the set, which effectively means they're both contending for the same row within the cache. We can only have one of these indices be resident in the cache. So what happens in this case? What we do is we select one out of all potentially contending indices uniformly or random, in this case just one, and cache that in the cache, and deem the other embeddings, are just in this case, again, just one of them, the index 4, to be a victim. We have to remember though, that 1 and 4 are both required to be in the cache to proceed with forward propagation and backward propagation. We only have 1 in the cache right now, and we still need to bring 4 into the GPU. So the way we do this is through a demand fetching mechanism during forward propagation. So essentially, again, we get a batch during training, look up in the occupancy table what indices are hitting and missing. In this case, as we can see, 1 has made it to the cache, so the occupancy table is letting us know that it's in the cache, whereas 4, which became a victim, is not in the cache. In this case, what we do is during forward propagation, demand fetch the embedding for 4 from the CPU resident embedding tables and cache it into a victim table, which is an auxiliary structure we maintain in GPU memory. Once we've demand fetched victims, all embeddings necessary for the next batch are in GPU memory. And thus, from this point on, the forward plus backward for this batch is GPU contained. I'll skip the details of flushing, which can be found in the paper in the interest of time, but essentially it's just done to make room in the victim tables for subsequent victims. So as I mentioned, the accuracy of a system is important. Often anything above a 0.05% of an error is often unacceptable and usually leads to considerable loss in revenue. The nice thing is our system actually doesn't lead to any loss in accuracy, as we can see on the 2 public data sets that we evaluated on, which is nice and makes the system potentially viable solution, at least from an accuracy standpoint. With that out of the way, there's certain performance considerations that we'd like to look at, because there are a lot of parameters that can influence the performance. The most important of which is the trade-off between the cache size and the look ahead window size. As we can see in the plot on the right, on the left of figure 3A, there is a inflection point beyond which increasing the look ahead window size for a given cache size leads to degradation in performance. And this is as a result of cache misses, which is reflected in figure 3C on the right. Essentially, when the cache size is too small and we have too many entries and we're looking ahead too many batches, the potential for misses increases. And we have to resort to demand fetching, which adds overhead. Now, you might ask why we'd want to increase the look ahead window size at all. And that's what figure 3B is showing us, is that provided we have enough room in the cache, it always behooves us to choose a larger look ahead window size, because our entire implementation is heavily parallelized and vectorized, and we notice much better performance as we increase the look ahead window size and are able to leverage parallel hardware much more efficiently. It doesn't seem to be moving on to the next slide. Well, I guess the only other slide that I had, there seems to be some kind of technical difficulty with it moving on. The only other slide that I had was showing how the system can scale when we have multiple GPUs available, since fundamentally this solution enables us to train large recommendation models on a single GPU, regardless of the model size. All we have to do is restrict the cache size to fit within the GPU. Because of that, when we have multiple GPUs, we can scale data parallelly across multiple GPUs to achieve better performance. So in the interest of time, I will refer everybody to some of the intricate details of the data parallel implementation in the paper. Happy to answer any questions that you might have. Okay. Apologize if this was a bit
Thank you very much. Thank you. So again, we've just time for a couple of questions. None in the audience at the moment, but a very straightforward question online. Is there a library or a code available that we can download straight away?
Yes. Yes, that was actually my last slide, was a link to the code, and then for some reason it didn't skip to that slide. So
here we go.
I will...
We have it up now. Okay, very good. I was interested in your locality of access point that you made, and I wondered whether the parameters of your caching algorithm, again, depend on the data. If you've got very skewed data compared to very sparse data, for example, does that affect the right parameters for your look ahead and cache size and so on? Like, can I configure this?
Yeah, so what we notice is that when parameters are sparse, that actually that kind of situation lends itself to our system. So yes, I do get that when we have locality, it is when that we might not have to actually look ahead. Looking ahead is only a solution to knowing what to put in the cache, because we don't have this reliance on locality of accesses, right? But in general, yes, it is data dependent, to answer your question. But what we noticed from the data that we've looked at is that the accesses do seem to be random and sparse. So without looking ahead, there is no notion of caching as something that we might use now might not necessarily be used later unless we know that it's going to be used later, if that answers your question.
Okay. Just one last question, and there are another couple of questions online, so do have a look at the stream. But you mentioned in your paper that 25% of the execution time is taken through cache management, if I understood that right. Do you have ideas for how you can reduce that proportion of time?
Well, so one idea we've been investigating to reduce the cache management time is to actually allow some slack in the training. And what I mean by that is right now, caching is being done sequentially to training. While the prefetching process is still prefetching and populating the queue, look-ahead queue with embeddings, the cache plus training process is still sequentially pulling from that queue, caching, and then proceeding with the training. One natural extension to this would be, how can we make sure that the GPU is directly populated before the caching plus training process is ready to use the next set of embeddings, right? Instead of having that process itself pull from the queue and cache. So we've been investigating how we could use copies of the caches to make two copies of the caches in GPU memory, where we essentially are having potentially the prefetching process also take on the responsibility of caching, where it caches into a backup cache in GPU memory, which isn't being used since we wouldn't want to interfere with parameters that are being updated by the training process, and then switch over to the newly updated backup cache for the next set of batches, and essentially toggle between what's being used and what's going to take in future embeddings. Now, obviously, the details associated with that, which we'd have to iron out, like hitting indices in the currently active cache and moving them over to the backup cache at the end of each switch. But this is a direction that we're looking at.
Okay. Okay. Thank you very much, and have a look at the stream for other questions. Okay. Thank you.
Thank you all.